Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 8th, 2025, and we're diving into an ICLR conference paper published a little over 3 months ago on January 22nd. It's titled DSPO, Direct Score Preference Optimization for Diffusion Model Alignment. This paper tackles making AI image generators, specifically text-to-image diffusion models. These are AI systems that create pictures from text, better align with human preferences. It introduces a new algorithm, Direct Score Preference Optimization, or DSPO. DSPO uses a technique called score matching, which essentially helps the AI learn an internal guide for what makes a good image, to fine-tune these models directly towards what people like, avoiding complex reward systems often used in other methods. Alright, so the paper kicks off by showing us a striking collection of images in Figure 1. We see a diverse set: portraits, animals, landscapes, even some sci-fi and fantasy scenes. These were all generated by Stable Diffusion version 1.5. That's a well-known text-to-image diffusion model, after it was fine-tuned using their new direct score preference optimization method. Fine-tuning, in this context, means taking an already trained AI and tweaking it to get better at a specific job. Here, it's about making images people prefer. The claim is these images not only stick closer to the text prompts, the descriptions given to the AI, but are also just more visually appealing thanks to direct score preference optimization. Building on that, Figure 3 gives us a look at the direct score preference optimization model framework. This approach is an alternative to methods like reinforcement learning from human feedback, or RLHF, which can require complex reward models. Direct score preference optimization is inspired by direct preference optimization, or DPO, aiming for more direct learning from preferences. This diagram shows two key processes. The top is the text-to-image diffusion model generating an image. The bottom is a target process incorporating human preference, quotes, Y. The backquote L_DSPO backquote is the crucial learning step, aligning the model's internal guide with this human-preferred target. Okay, so moving to the results, Figure 4 presents several bar charts. These charts compare the performance of direct score preference optimization, that's the method shown by the red bars, against other approaches. These include the original Stable Diffusion version 1.5 and other preference learning techniques like Diffusion Direct Preference Optimization. They are evaluated using different metrics such as pick score, human preference score V2, and aesthetic score, which all essentially measure how much people prefer the generated images or their visual appeal across different image datasets. And, consistently, direct score preference optimization achieves the highest scores, showing it's really effective. Now, after seeing those strong performance results, you might wonder about the cost. Table 3 addresses exactly that, detailing the computational costs. It compares direct score preference optimization with diffusion direct preference optimization in terms of training time per step and peak GPU memory. That's the amount of specialized computer memory needed by the graphics processing unit, which is a powerful chip for these tasks during training. The numbers are really close. 4.18 minutes for direct score preference optimization versus 4.15 for diffusion direct preference optimization, and GPU memory usage is also very similar. This similarity in resource demand shows that direct score preference optimization achieves its better performance without significantly demanding more resources. So while the computational demands are similar, Table 1 here really drives home the performance advantage. This table presents a win rate comparison, essentially how often one model's output is preferred between direct score preference optimization and other methods like supervised fine-tuning, or SFT, and diffusion Kahneman-Tversky optimization, or diffusion KTO. These are evaluated against the original Stable Diffusion version 1.5 using various reward models, AIs that predict human preference, like PickScore and CLIP, a model judging text-image alignment. Across different datasets, direct score preference optimization, shown in bold, consistently scores highest, reinforcing its superior ability to generate preferred images. The previous table showed direct score preference optimization's strength against Stable Diffusion version 1.5. Now, Table 2 extends this, comparing win rates when these methods are applied to SDXL. That's another powerful text-to-image diffusion model. Across datasets like PIC-V2 and Party Prompt, and using familiar reward models such as Human Preference Score V2 and CLIP, direct score preference optimization consistently shows high performance, often leading the pack with those bolded numbers. This adaptability to different base models like SDXL really highlights the robustness of the direct score preference optimization approach, which cleverly aligns model objectives using score matching, a method that helps the AI learn the underlying patterns of preferred images. Okay, so direct score preference optimization isn't just good for generating images from scratch. Table 4 here shows its performance in text-guided image editing, which is when you ask the AI to change an existing image using text commands. This table uses the InstructPix 2Pix dataset and compares direct score preference optimization with methods like supervised fine-tuning. Across metrics like PIC-score and CLIP, direct score preference optimization, highlighted again, consistently achieves strong results, often leading. This performance in image editing really underscores the versatility of the direct score preference optimization approach for different image manipulation tasks. So, wrapping up our look at direct score preference optimization, it's clear this method offers a strong new approach for aligning text-to-image diffusion models, those AIs that generate images from text descriptions using a gradual refinement process, with human preferences. The key seems to be its ability to harmonize training objectives through score matching, leading to better results without the overhead of separate reward models or much higher computational cost. It's a promising direction for making AI-generated images even better. That's all for this paper. Thanks for joining the AI Research Roundup.